Hey guys, it's Rue, and this is number 5 from chapter 4. A fish swimming in a horizontal plane has velocity v equals 4I plus 1j meters per second at a point in the ocean where the position relative to a certain rock is r is equal to 10I minus 4j meters. After the fish swims with constant acceleration for 20 seconds, its velocity is v equals 20I minus 5j meters per second. So part A of the problem says, what are the components of the acceleration?
So for this problem, drawing a picture isn't really that helpful, but let's go ahead and do it anyway. So you have your fish over here, and you have a rock over here, and it's swimming in this general direction at a velocity of 4.0I plus 1.00j meters per second.
Okay, so for part A, we're looking for the components of acceleration. So for this, you can use your kinematics equation. You have final velocity is equal to initial velocity plus acceleration times time. And so now you can just move around your variables so you get acceleration on one side. So you'll get acceleration is equal to final velocity minus initial velocity over time. And then when you substitute everything in, you can substitute in the final velocity which you're given, which in this case is 20-5 meters per second. And you subtract the initial velocity, which is 4.1 meters per second. And that's all divided by your time, which is 20 seconds. And when you calculate that all out, you're going to get a vector, you're going to get an acceleration vector of 0.8 and -3j meters per second squared. So that's your part A. This is your components of acceleration.
So now for part B, they're asking you to find the direction of acceleration with respect to the unit vector. So the unit vector I. So the unit vector I is just a magnitude of 1 in this direction, and it's obviously in the I direction, which is kind of like the x component. So you're finding the direction between this vector and the vector that we found over here, which was the acceleration vector. So if you draw it out, you have your unit vector going directly to the right, and since your acceleration vector is 0.8 -3, it's going to be going in this direction. So this is your acceleration vector, and you're looking, pretend these like extend all the way, you're looking for this angle right here. So since you know this value, you know the x value and you know the y components of the acceleration vector, you can just use a right triangle and find theta in that way. So if you do tangent theta, so you know that this x value is going to be -0.3 and this y value is -0.3 and the x value is 0.8. So if you just use tangent theta is equal to your opposite over adjacent, which is -0.3 over 0.8, and then you plug that into your calculator with inverse tangent, and you're going to get theta is equal to -20.56 degrees. And the answer in the book wants you to go counterclockwise. So this is equal, if you add 360 to it, this is equal to 339.44 degrees, and I think in the book they just round to 339 degrees. So this is the direction with respect to the unit.
For part C, it says, if the fish maintains constant acceleration, where is it at t equals 25 seconds, and in what direction is it moving?
So there's essentially two parts to part C. You have to find the position vector to find where it is at t equals 25 seconds, and then you have to find the direction, which is an angle. So for the first part, for the position vector, you can use another kinematic equation, which is going to be change in x is equal to initial velocity times time plus 1/2 acceleration times time squared. And since you're solving for the change in x, you don't have to move any variables around. You can just plug everything in. So you know your initial velocity is going to be 4,1 meters per second, and you're multiplying that by the time, which is 25 seconds. And then you're adding 1/2 times acceleration times time squared, which is going to be 1/2 times your acceleration you already know from your part A, which is going to be 0.8 comma negative 0.3 meters per second squared, and that's going to be multiplied by time squared, which is going to be 25 seconds squared. And if you multiply that all out and you add it together, you have everything written out. You just plug that into your calculator and you're going to get your position back. So when you do multiply and add that all out, you're going to get equal to 350 negative 68.75 meters. But that's actually going to be your change in x, and we're actually trying to find the final position. So you know that your initial x, or your initial distance position, is going to be 10 comma negative 4, because you know that's in relation to the rock which we drew somewhere back over there. And you know that final position minus initial position is going to give you your change in position. So you know this value and you know this value, so you're solving for your final position. So you move everything around and you get your final position on one side. So your final position is equal to the change in x plus your initial position. So you just add those two vectors together, which is going to be 350 negative 68.75, and you add that to your initial position, which is going to be 10 negative 4, and when you add that all together, you're going to get a final position of 360 comma negative 72.75. So putting that into your answer, you're going to get a final position vector of 360 I hat minus 72.5 or 72.75 j hat, or some version of that, rounded depending on where you rounded and how much you rounded, meters. So this is part of your answer for part C. For the second part of part C, they're asking for the direction when the time is equal to 25 seconds. So for this, you're going to have to use your velocity vector, and you're looking for your final velocity, like what direction or what velocity is it moving at 25 seconds. So again, you can use your kinematic equation, which is going to be final velocity is equal to initial velocity plus acceleration times time. And you just plug in your initial velocity, which is 4,1 meters per second, add it to your acceleration, which is 0.8 negative 0.3 meters per second squared, times time, which is 25 seconds. And then when you multiply and add that all out, you're going to get a final velocity of 25 negative 6.5 meters per second. So if you were to draw this out on an axis, it would look something like this. So you're going 25 meters per second this way, and you're going negative 6.5 this way, so your velocity is going to be in this direction. So you know that your x component is 20, I'm sorry, this should be 24, my b. This is 24, so this is 24, and then your y component is negative 6.5. And you're looking for the direction, which in this case is this angle right there. So here you can use tangent theta is equal to your opposite over adjacent, which in this case is this is your opposite over your adjacent. So negative 6.5 over 24. You plug that into your calculator and you get theta is equal to negative 15.15 degrees. I think the book rounds it to negative 15.2. This is your direction, and I guess you can add 360 to that to get a positive angle if you really want to. So that is number 5.